Welcome to a course designed to equip future electrical engineers with something more than formulas, the mathematical mindset to model, analyze, and solve real engineering problems. At its core, this course focuses on one of the most essential tools in engineering: differential equations. The primary goal is simple, yet fundamental: to give you the skills needed to understand and manage how electrical systems behave over time. Whether you're dealing with voltage fluctuations, control feedback loops, or signal behavior, differential equations are how we translate physical systems into mathematical models. More importantly, this course aims to help you develop the ability to carry out true engineering analysis with clarity, precision, and purpose. By the end of this journey, you'll be able to do much more than solve equations. You'll start by learning how to model and classify different types of ordinary differential equations based on their order, linearity, and homogeneity. You'll practice translating real physical systems into first and second order ODEs that describe how those systems evolve. Next, you'll dive into analytical techniques, learning how to solve first-order equations using separable forms, integrating factors, and exact methods. For second-order linear equations, you'll use methods like undetermined coefficients and variation of parameters, powerful tools for tackling real circuit dynamics. From there, you'll step into the world of Laplace transforms. You'll explore how this elegant mathematical technique allows us to solve initial value problems, analyze system behavior, and even determine transfer functions in circuit and control analysis. But systems aren't always isolated. You'll also learn to analyze systems of differential equations, particularly using matrix methods like eigenvalues and eigenvectors to model interconnected or coupled components in complex electrical systems. Beyond theory, you'll apply what you've learned directly to core areas in electrical engineering, including RC, RL, and RLC circuit analysis, basic control system design, and essential signal processing tasks. These applications turn abstract math into practical engineering insights. To tackle more complex or real-world systems where exact solutions are impossible, you'll use numerical methods like Euler's and Runge-Kutta techniques. You'll also gain hands-on experience using computational tools like MATLAB or Python to simulate and visualize dynamic behavior. Finally, this course emphasizes critical thinking. You won't just solve equations, you'll interpret them. You'll question whether a solution makes physical sense, visualize it, test edge cases, and analyze key system features like stability, transience, and resonance. By mastering these outcomes, you won't just become a better problem solver. You'll become an engineer who sees the invisible patterns behind every signal, every response, and every system. And that, truly, is the power of differential equations.